All right, so for today's kind of seminar, we're really happy to have Ryan Thorngren from Harvard. Ryan has been doing a lot of really interesting work recently on using and really extending techniques like symmetries and anomalies to study QFTs non-perturbatively, in particular with applications to gapped and gapless phases of matter. So we're really happy to have Ryan, and whenever you're ready, take it away.
Thank you, Luca, for the introduction and for the invitation. It's very nice to be here and share with you this interesting work, which really most of the credit goes to my wonderful collaborators, Dominic Ellis and Senthil at MIT. And if I wanted to summarize this work, well, it's about Luttinger's theorem, which is a very classic result in solid state physics that I feel like we understand very well. And I'm sure there are people in the audience who have a much deeper understanding of it than I do. But at the same time, in recent years, because of the study of SPT phases and topological insulators, we've learned a lot more about anomalies. And there's a sort of business of taking classic theorems about condensed matter and solid state physics and high energy theory and recasting them in the light of anomalies. So that's what I'm going to try to do in this talk. So it's a bit of a revisionist point of view, and I'll try to give as much background as possible. Feel free to interrupt me if you have any questions. And before I forget, let me just set a timer so I know what time it is. Okay, so without further ado, so what I'll do is I'll review Fermi liquids for you. Try to keep it brief and painless because it'll be boring to some of you for sure. And then I'll get into the meat, which is to explain how Luttinger's theorem is a kind of anomaly matching condition between the microscopic lattice model and the sort of infrared continuum limit. And I'll explain this in a couple of examples, namely the 1D Luttinger liquid, where the Luttinger's theorem is basically given by the famous chiral anomaly. And then in 2 dimensions, where there's a generalization of the chiral anomaly, but one has to enlarge the concept of the symmetry group to something called the loop group. And finally, if I have time, I'll talk about a no-go theorem for compact symmetry groups, which tells us that if the filling is not a rational number, then the symmetry group must be non-compact. So this is an interesting no-go theorem for reasoning about effective field theories of systems with irrational filling, especially metals, which can exist at generic filling. Okay, so let's begin by talking about band theory. Band theory applies to systems with a U1 particle number conservation or charge conservation and a lattice translation symmetry. So a typical Hamiltonian that has the symmetry would be the Hamiltonian of a fermion hopping on a lattice. So if we have some fermion creation and annihilation operators A, we can write this hopping operator that takes a fermion at site J and puts it at site I and give it some coefficient Tij and study this Hamiltonian. So it's probably the simplest many-body Hamiltonian one can study. And it's solvable. The way to solve it is to go to the Fourier basis. So when we do a Fourier transform, this sum over the lattice becomes an integral over a torus. That torus, here little d is the space dimension. So this is the Brillouin zone, or BZ, and it's expressed in terms of creation operators now in momentum space, where we have an operator that annihilates a fermion of momentum k, which is expressed in terms of the lattice operators like so. And in terms of these operators, the Hamiltonian is basically an integral of a number density. So there's an operator that measures the occupation number of momentum k, right? So this operator is 1 if there's a fermion of momentum k, 0 otherwise. And the coefficient that comes here is therefore called this is the single particle spectrum. Because if we imagine there's a single electron in the system and it's in an eigenstate, what it does is it just has some momentum k and some energy epsilon k. And it's useful to draw the single particle spectrum. So it forms some periodic function of k. So here's k, and it'll be periodic. So we don't have to cut it off at some periodicity, 2 pi over the lattice spacing. And epsilon forms some typical periodic function here. And if we want to describe the many-body ground state of this system, all we have to do is specify how many electrons there are. Because as we start with an empty system, and then we add electrons one by one, they'll find the lowest unoccupied state and fill it. And we'll keep filling up to some Fermi level. And the Fermi level determines whether the ground state is gapped or gapless. For instance, if the Fermi level is, say, up here, above this band, and maybe there are more bands that it doesn't intersect, that this ground state is gapped. That's because the minimum energy excitation, what you do, all of the states here are filled, all of the states here are empty. You take the highest energy filled state, which is maybe over here, and kick that electron into the lowest energy unoccupied state here. And because of this band gap, that has some positive energy associated to it, so this is a gapped ground state. On the other hand, if the Fermi level crosses a band, then we're going to have a gapless system. And that's because there are filled and empty states of arbitrarily close energy, right? There's a filled state very close to the Fermi level here and an empty state very close to the Fermi level here. And so we have excitations above the ground state of arbitrarily small energy. So this is a gapless state. Okay, so depending on the Fermi level, the many-body ground state can be quite different. Now, an important invariant that is going to be the central player in this talk is the filling fraction. The filling fraction is defined simply by the number of electrons in the system per unit cell. We're dividing by the number of unit cells so that we don't have an extensive quantity and we have something that makes sense in the thermodynamic limit. And we're going to be interested in how this filling fraction nu constrains the long-range behavior in the thermodynamic limit. So importantly, it really only matters to us mod 1 because we can always have some extra band at very, very low energy, which is filled. And this band, we can kind of integrate it out in perturbation theory. It's not going to interact very strongly with any of the modes near the ground state because those are all at a much higher energy scale. So the important result about the filling fraction is that nu equals the fraction of the Brillouin zone enclosed by the Fermi surface. So in this picture here, where we have a Fermi level that cuts through a band, we have what's called a Fermi surface, which is defined by where this band intersects the Fermi level. And the volume enclosed by the Fermi surface here is just this length, the difference in momentum between these 2 points in this one-dimensional picture. So Luttinger's theorem says that this length equals the filling fraction, the charge per unit cell. If we had a 2D system, the picture is a little bit harder to draw, but we're going to have two momentum coordinates. And now the bands form surfaces, and the Fermi level will cut bands generically along a curve. So now the Fermi surface will be this curve. And Luttinger's theorem tells us that the area inside equals the filling fraction. So a simple corollary of Luttinger's theorem is that if the filling fraction is non-zero, or really not an integer, then the ground state is non-trivial. It can't be a band insulator. You need to have, in these pictures, Luttinger's theorem says that there's a Fermi surface. So in particular, it's gapless, but at the very least, it's non-trivial. So this is a very modest corollary, but already it's quite interesting. And we would like to know if this corollary persists, if it remains true in systems more general than Fermi liquids, or more general than you can access by perturbation theory around Fermi liquids. So in particular, we're interested in maybe non-Fermi liquids, metallic states that exist at generic filling fraction, but which we don't know how to define a Fermi surface.
For this definition of, or for this statement of Luttinger's theorem, do you have in mind a particular definition of Fermi surface in an interacting system?
No, so this statement is like I don't mean it to be fancy at all. It's just a statement about Fermi liquids at the moment. So eventually I'll give you a statement that doesn't really look like Luttinger's theorem, but I'm going to tell you that it really is Luttinger's theorem, but it makes sense even when there's no Fermi surface.
Okay, I guess what I'm getting at is that in the original Luttinger paper, he has a particular definition that makes sense in the context of perturbation theory. And the statement is true for that definition. But for non-perturbative arguments, one is probably working with a different definition.
Yeah, and I'll get to something which looks like a definition of Fermi surface. But actually, the theorem that I'll state is more general than systems that have Fermi surfaces.
Okay.
Okay, thanks for the question. Now, the program is to try to think about Luttinger's theorem, or at least this corollary, as a kind of 't Hooft anomaly for the symmetry. Now, I'm going to tell you about 't Hooft anomalies, but just to give you some intuition for why you might make such a claim. First of all, 't Hooft anomalies, any theory that has a symmetry, a further invariant of a global symmetry, the further invariant of that symmetry is the 't Hooft anomaly. And the important result about 't Hooft anomalies is that there's a UV-IR matching. So that if we have some anomaly in the UV, and then we undergo some symmetric RG flow, so an RG flow triggered by a symmetric operator, flow to some IR fixed point, the anomaly in the infrared has to equal the anomaly in the ultraviolet. In particular, if the anomaly in the ultraviolet is non-trivial, right? If the left-hand side is non-zero, then the right-hand side is non-zero. And that tells us that the ground state cannot be trivial. Trivial in the sense of non-degenerate, gapped. Such systems have trivial anomalies, so they can't be the result of RG flows from microscopic theories with anomalies. So that's what we want to say the filling fraction is. We want to say that the filling fraction, by its definition, this is like the UV anomaly. It's a microscopic quantity, the charge per unit cell. And we want to say that it constrains the ground state, some kind of long range IR property. For instance, by saying that if nu is not an integer, that the system is gapless. Some kind of statement like that.
Do you want this to be an anomaly in what?
So it's going to be an anomaly for the global symmetry U1 times translations.
Okay.
So I want you to think about this as quite analogous to the Lieb-Schultz-Mattis theorem. In fact, that analogy was exploited by Oshikawa in this great paper, where he gives a flux threading proof for a version of Luttinger's theorem and a version of the Lieb-Schultz-Mattis theorem sort of all at once. And now, to remind you what the Lieb-Schultz-Mattis theorem is, this tells us that a spin 1/2 chain, so just some one-dimensional lattice where each site has a spin 1/2, that the ground state of this system, so long as the Hamiltonian preserves spin rotation and translation symmetry, that the ground state is either gapless or it has some spontaneous symmetry breaking. In this case, translation symmetry can break, for instance, by spontaneously forming singlet dimers. So this Lsm theorem has been understood in terms of an anomaly, and I'll get to that. And so the essence of the Lsm theorem is that at each of these sites, we have a spin 1/2, which we can think of as a projective representation of the spin rotation symmetry SO3. And this projective representation for unit cell is one way to talk about the anomaly. Now you might say that, well, it's a projective SO3 representation, but not a projective SU2 representation. But actually the center of SU2 acts by a scalar matrix in this theory. So as far as the symmetry on operators is concerned, the symmetry is SO3. So this is an SO3 times Z anomaly. Okay, I want to tell you about that, but first I have to tell you.
Can you go back, Ryan? The center of SU2 doesn't act site by site as -1 on each individual spin. Why?
Yeah, it does, but that's like a scalar matrix, so it doesn't act on operators.
A spin doesn't count as an operator in this. What counts as an operator?
What do you mean? No, it would act by conjugation on operators, and conjugation by basically the central element of SU2 acts by -1 to the number of sites, right? So it commutes with everything. Do you agree?
Maybe we should talk about this point later. I think I'm confused about something pretty basic, but probably
There's only spin 1/2s at each site. It's not like you can occupy it with a spin 0 or a spin 1/2. Then it would be a real symmetry. Anyway, let's chat about it later. But this reminds me that the relationship between, or at least the intuitive relationship between Lsm and the Lieb-Schultz-Mattis is that instead of having something like a spin 1/2 per unit cell, in Luttinger we have sort of a fractional charge nu per unit cell. But the issue with this is that there's not really a good U1 representation that you can talk about to call this fractional charge nu, whereas we had this spin 1/2, which is a bona fide projective representation of SO3. U1 has no projective representations. And that's going to cause a problem for us trying to interpret Luttinger's theorem as naively as an anomaly. Okay, but to tell you more about that, I have to tell you more about anomalies first. So one way to think about an
Ryan, the
anomaly.
one you're talking about acts on all the A's with some fixed charge. Is that what you're?
That's right. Yeah, it's just the particle number.
Overall particle number. Okay.
Sorry about that. Hopefully you can hear me. Oh, wait a second. Okay. So the best definition of a Hooft anomaly is that it's an obstruction to gauging the global symmetry, where gauging means that we take our correlation functions, our partition functions, whatever we have, and we define them also in the presence of a background gauge field. And we want to do so in a way that everything is gauge invariant. So for example, we want to be able to define the partition function on a spacetime with some background gauge field A, such that if we perform a gauge transformation, that the partition function doesn't change. And what we're allowed to do is we're allowed to add local counter terms in order to achieve this, right? So we might have some action that just depends on the matter fields, and then we have some kind of minimal coupling to the gauge field by some current, all right, some kind of JA, and then we might add more local counter terms. But if we can't achieve gauge invariance by arbitrary local counter terms, then we have an anomaly.
Ryan, what is our working definition of local counter terms since we have a lattice system here?
No, so let me not talk about the anomaly on the lattice. Let me just talk about the anomaly in the continuum limit for now. That's actually the only thing that I'll use. So for a moment, we're thinking about field theory, right? So gauge invariance, if gauge invariance is not achievable by local counter terms, which really is just, whatever your, any local operator should allow any local operator here, so long as it's 0 when you turn off the gauge field, so you haven't actually changed the theory.
Even more, right? We allow gauge non-invariant things there.
That's right, yeah. You only want the combination to be gauge invariant. And if you can't make the combination gauge invariant, then we have an anomaly. But in that case, there's still something you can do. And that's to use this trick called Anomaly Inflow, which is that even if ZXA is not gauge invariant, it may be, actually it is in all situations that we know about, that there's some theory that we can define, or not really a theory, but some topological term that we can define on a manifold of one higher dimension. So here Y, some bulk space-time that our anomalous system sits on the boundary, that this combination is gauge invariant. So if we can do this, then we're quite a ways along in understanding what the anomaly is. What we can do is we can think about this topological term as the effective action of a d+1 dimensional SPT that our system sits on the boundary of. So the picture in general is that we have some d+1 dimensional SPT with a boundary, and we have our anomalous system on the edge. So this gives us a correspondence between anomalies in d dimensions and SPTs in d+1 dimension. So for instance, the Lsm theorem is associated with the Haldane SPT as follows. So as a baby case, consider a system in 0 plus 1 dimension, so just a spin 1/2 particle, and we couple this to an SO3 gauge field, and we'll show that you can't do this in a gauge invariant way. And basically the reason, if you think about the world line of this particle, so it travels through some S1 world line, gauge transformations are going to be maps from this S1 into SO3. And there's one particularly interesting class of maps, which are maps that wrap the fundamental group of SO3. In particular, they're maps where as you go around the circle, you're not really doing anything, and then at one point you do a 2π rotation. So that's a gauge transformation. But the system is going to transform under this gauge transformation because it's in the spin 1/2 representation. So this partition function, this is computing something like a trace e to the minus beta h. And then when we do this gauge transformation, we're inserting this 2π rotation into this trace, and it's a spin 1/2 Hilbert space. So the 2π rotation acts by minus sign. And there's no way to get rid of this minus sign. By a local counter term. Now you can try, but how do you really know? And the only way to really know is to use this anomaly inflow picture, is to realize that if we place this circle on the boundary of some surface, doesn't matter what kind of surface, and we place the following expression here, e to the I pi integral, so let's call this surface y, as we did, of a quantity called W2 of this SO3 gauge field. Okay, so now the SO3 gauge field is defined not just on the boundary, it's defined everywhere on the surface. There's some invariant of the gauge field, which is a kind of traced curvature called the second Stiefel-Whitney class, or W2. And this class has the property that when we perform this large gauge transformation, at the boundary we get a minus sign, given by the winding number around SO3. So the combination is gauge invariant. And the way we know for sure that you cannot have gauge invariance just by some local counter term is by showing that this quantity, this has an integral on a closed manifold. In particular, if we just have a two-dimensional sphere, we can define an SO3 gauge field here that contains a 2π flux, or contains a monopole, so that there's a 2π flux through the surface, that the partition function of the SPT on this sphere is -1. And now, if we were able to cancel, if we were able to make the boundary theory gauge invariant by local counter term, then this integral would have to be 1, or this partition function would have to be 1. So that's one way to see that there really is an anomaly. So the steps are find a bulk topological term that so that the combination of bulk and boundary is gauge invariant, and then find a manifold on which the topological term is non-trivial. Okay, so turns out that this is the partition function of the spin 1 Haldane phase. There's a famous SPT that has a spin 1/2 at the boundary. So that's just another way of saying what I just described to you. And if we wanted to describe the Lsm theorem as an anomaly, the bulk SPT associated to it would just be an array of these SPTs, where each of the wires of this array ends, we have a dangling spin 1/2. So here we have our Lsm anomaly at the boundary. And there's also a topological term associated to this array, but we have to consider now the full symmetry. SO3 is not enough. Now we have to remember that there's translation as well. And the way to do it is we have our SO3 gauge field A as before. We need to add something like a Z gauge field. So let me call it tau. Tau is basically a real one form whose integral over closed loops is an integer. And the anomaly action for the Lsm theorem is pi times tau wedge W2 of A. And you can also find a manifold, say S1 times S2, on which this has a non-trivial integral by taking tau1, or taking tau to have holonomy around S1 and W2 on S2 as before. Now, what makes this really an anomaly is that this coefficient is quantized. This is a problem when, say, we break the SO3 to U1. If we were to just consider spin rotation symmetry around a single axis, then we would no longer have an anomaly because this coefficient in front would be continuously tunable. And there would be no reason why the bulk, say if a bulk had such a topological term, there would be no reason why it had to have a non-trivial boundary, because you could just continuously tune the coefficient of the topological term to 0 as you reach the boundary. And that's related in the classification of SPTs, that there's no U1 times Z to the D SPT. And that's for the same reason why there's no projective symmetry for U1.
So Ryan, I'm a bit confused about the continuum limit versus the lattice discussion here. So we're kind of using continuum description like along the wires, but lattices in the array. Is that how I'm supposed to think about this? Like you didn't write you didn't make the whole system continuous at the end. You still remember.
No, but let me do that now, because now I'm going to talk about how, we can find the anomaly, but we have to leave the lattice behind. So that's one reason why I didn't. There is a way to make some sense of, say, a translation gauge field, but it's not very enlightening for the purposes of this talk. And okay. I suppose you could also, right. Well, let me address that now, hopefully. So instead of saying that there's some U1 times Z to the D anomaly, which people have tried to say that there's something like a non-quantized anomaly, instead I'm going to talk about an emergent anomaly for how these symmetries act in the continuum limit. So what's going to happen is that in the continuum limit, all interesting symmetries, well, I shouldn't say all interesting symmetries, but translations, they give rise to an internal symmetry.
So can I ask you a quick question, Ryan?
Yes.
So on the lattice, there isn't even a unitary operator that implements the translations, is there? Like in the continuum, you can just sort of exponentiate the derivative or the momentum operator, but on the lattice, you can't do that, right?
What's wrong with just the sort of permutation operator that just takes every site, you know, one step to the right? That's a unitary operator. It's not a finite depth circuit, but it's unitary.
Cool. Thanks.
Okay. But yeah, in the thermodynamic limit, you can be skeptical about this. Okay, but in the continuum limit, if we think about in terms of the fields, when we do a translation, phi of x transforms to phi of x plus a, along with some unitary rotation, or maybe I was calling it little l. Let's call the lattice spacing little l. But in the continuum limit, we're going to be taking the lattice spacing to 0. So to order L, it's actually an internal symmetry. And as L goes to 0, this transformation, I was using dagger here, this transformation becomes a bona fide symmetry of the continuum limit. And the way we can express this in general is we say that there's some symmetry GUV of the microscopic theory. So in our case, it's U1 times z to the d. And then there's a map into the infrared symmetry group. So this is all microscopic symmetries. And these are internal symmetries. And what I'm going to argue is that the filling fraction implies an anomaly here. So we want to show GIR is anomalous if nu is not an integer. So this will allow us to sidestep issues of trying to understand gauge fields for crystalline symmetries, and also these issues of quantization in the microscopic symmetry.
Can I ask some questions? So it seems like a big translation in the lattice should map to a translation at long distances. So why does that not happen?
Right. So big, I mean, it's the generator is close to a symmetry. So the square of the generator is a little bit less close to the symmetry, maybe. And you could be worried about this, but I think in the limit, you just get a symmetry.
But I'm confused about the double counting. Are you saying that the lattice translation in the ultraviolet gives rise both to translations and to an internal symmetry at long distances?
No, so what I'm saying is that in the continuum limit, well, I have to be careful, but yeah, there is some kind of like duplication of symmetries happening where there will be like a kind of trivial translation that just moves the fields from one part of the system to the other. And if the system is isotropic, you expect to have that and maybe even like a Lorentz symmetry or Galilean symmetry that's emerging in the continuum limit, and we'll have continuous translations. But then you'll also have the microscopic symmetry. Now, the microscopic symmetry could end up acting trivially. So this map could be trivial if the microscopic translation is not interesting enough. if it is interesting, for instance, in like an antiferromagnet, what's going to happen is that the translation is going to map to a spin flipping, because that's what microscopically it looks like with respect to the antiferromagnetic pattern of, like, you know, in some nail state up down. Then you see that a translation involves a spin rotation.
Let me understand a slightly different example. What about a situation on the lattice with a discrete rotation invariance?
So there, I cannot make this argument about the Taylor expansion of phi, right?
Right. Then it looks like you're moving things very far away.
Mm-hmm.
And does that also give rise to an internal symmetry, or just the naive rotation symmetry at long distances?
So in practice, it often does give rise to an internal symmetry, but I don't really see like a general reason. If you expect some continuum rotation symmetry to emerge, then I think you expect that like there will be a trivial rotation that you can multiply by the microscopic rotation in order to get an internal symmetry.
Mm-hmm. And the second thing is that I'm generally suspicious about claiming that anomalies for emergent symmetries obey any matching. In general.
Oh yeah, well, I'll argue why. I'll tell you why. So,
like, there's no universal theorem like that, though.
No, there's no universal theorem. But here there's something very specific that happens.
Okay.
So let me get to that. And so
okay.
that's this point here too. The second bullet point here. So the filling fraction appears as a projective symmetry action. So I said there's no U1 projective symmetries. In this case, we have a projective symmetry of translation on the 2 pi flux. And what that means is, if we consider a region where there's magnetic flux 2 pi, and we perform a translation on this region, so I'll just draw the translations as really large, but it doesn't matter how big they are compared to the flux. We do an X translation, a Y translation, a minus X translation, and then a minus Y translation. Then we take this flux around a unit cell. And in a unit cell, there's a charge nu, right? That's the definition of the filling fraction. And so what we would get is an Aharonov-Bohm phase, e to the 2 pi I nu. So in terms of the translations, they don't commute when nu is not an integer and in the presence of a 2 pi flux. So this commutation relation is going to appear in the anomaly of the infrared symmetry. And in higher dimensions, there's going to be some generalization of this, but let me just focus on 2 dimensions for now. And one way to see that this commutator has to appear in the anomaly is to think about, well, let's think in terms of a partition function. So if we have the partition function of our 2 plus 1D theory on R times S2, right? So we have a small sphere here. We put the 2 pi flux on this sphere, then we also get to define gauge fields for the remainder of the symmetry, in particular for the image of the translation generators. So if I insert, so I better name the image of the translation generators. So let's take, so for instance, tau x, translation x is going to go to some generator. Let's call it x underline. Tau y is going to go to some generator y underline. And so we can define a gauge field such that it has a sort of delta function form where when you cross this point, the fields transform by x lower. And when you cross this point, they transform by y underline. Now, gauge invariance tells us that we can deform this gauge field so that these points cross each other. So this partition function would be equal to this partition function if the system were anomaly free, right? If the theory were gauge invariant. But we know this is not what happens if nu is not an integer, right? Because what we're doing is we're picking up the commutator of these two operators, right? And as we've said, the commutator has to be e to the 2 pi I nu. So what can we do about this? Well, one way to fix it is to put it on the boundary of a bulk theory. And when we put it on the boundary of a bulk theory, these points where the operators were applied become lines. And when we swap these points, these lines end up crossing. And now the bulk can solve our problems for us if it associates the phase 2 pi I nu to this crossing. And so this means, so this is a contribution to a topological term in the bulk. One way to think about topological terms is to just assign phases to these defects. And in particular, there's a partition function that sees this phase. It's a partition function on a closed surface by taking a torus times a 2 sphere. We put the 2 pi flux on this 2 sphere, and then around the torus, we put an x loop here and a y loop here. And we see that the partition function of the emergent anomaly on this closed manifold gives us the filling fraction. So in general, you can say, to recap, what we've done is we've defined some gauge field. So this picture with the 2 pi flux and the 2 loops defines a gauge field on this torus times sphere. And our condition, our anomaly matching condition, is that if we compute the emergent anomaly of the long range of the continuum limit on that background, that we get 2 pi times the filling fraction. So this is our main result, I'd say, and this is what should be thought of as the interacting version of Luttinger's theorem. You notice there's no reference to a Fermi surface anywhere here, but the corollary does follow that if nu is not an integer, then there has to be a non-trivial anomaly in the long-range limit, and in particular, the ground state has to be non-trivial. And then we can start to think about possible solutions to this anomaly vanishing equation in order to constrain the ground state given the filling fraction. And I'll pause for questions for giving an example.
Ryan, I mean, given that this is an anomaly that you formulate for an emergent symmetry, it seems that I could conceive of symmetry preserving deformations that preserve only the microscopic symmetry that take me outside of a phase that has this emergent symmetry and therefore breaks this matching. Right? That's generally speaking why anomalies for emergent symmetries do not match.
Well, that's true. You'll get some other anomaly, but you still have to solve this. This equation still has to be solved.
Formulate nu. I mean,
the point of this equation is that the anomaly tells you the commutation relation of translations on the 2 pi flux.
Only in the phase when the emergent symmetry is what you said it is. But I can conceive of...
No, it doesn't matter what the emergent symmetry is. It has to have some kind of translation generators in it.
let me give a different example, and you can tell me why this is different. So imagine we have like SUN gauge fields coupled to an adjoint scalar. And in whatever space-time dimension, doesn't much matter. In one phase, we let the scalar condense, and we get some U1 gauge fields, and they have an emergent symmetry, the standard higher form symmetry of Maxwell theory, and an emergent anomaly. On the other hand, completely consistent with the UV symmetries, I can mass up those scalars, let the gauge fields confine, and just end up with nothing. So there's just no matching under those kinds of deformations. There's matching provided the deformation of the UV preserves the emergent symmetry. But
well, I think you're getting hung up on this term emergent. The symmetry is not completely emergent. There is a microscopic symmetry, and what we're using is we're only using images of this map. And there, the symmetry will always match in all of the cases. Now, GIR can change, like you're saying, but normally, if these were both internal symmetries, we would say the pullback of the anomaly along this map from GIR equals the anomaly of GUV.
But then why do you even need to discuss GIR to begin with? Why can't you just phrase for me the anomaly for GUV?
Well, the problem is basically because of what GUV is. There's not really a good anomaly that we can write down for U1 times e to the d. Now, maybe there is a theory of anomalies that works for this group, but rather than like postulating a new theory of them, I just want to talk in terms of the
but doesn't the fact that you can't write an anomaly for the UV microscopic theory like suggest to you that this problem that I'm talking about is not just a technical one?
I mean, another thing that you can think about is that the filling fraction, it's really different from an ordinary anomaly in that you get to choose the filling fraction, right? Like in the many body Hamiltonian, I can study it at any filling. I can choose to put however many electrons in the system as I want. And you can worry that if you're too general and you allow the filling to be another parameter of your theory, that you won't see any of these anomalies. And that's true. And I think that's basically what the U1 times e to the d is doing. It's like not strong enough because the filling needs to be put in by hand. But here I'm saying that the way to put in the filling by hand for the continuum limit is to impose this anomaly matching condition.
Mm-hmm.
But I agree, it's a little confusing. Well, let me show you how it works for the Fermi liquids, and at least you'll see that it gives you Luttinger's theorem. So you can hope that there's some truth to the statement.
Can I say one thing about this?
Mm-hmm.
So I think the confusion is in referring to this as anomaly matching. I mean, the microscopic filling is not an anomaly. I mean, I think that's clear for any reasonable definition of anomaly. So in that sense, it's not anomaly matching, but it's matching of something that isn't an anomaly. So,
mm-hmm.
I mean, the microscopic filling, it may not be an anomaly, but it's still a very well-defined concept. I mean, there's no ambiguity there. And so we're just saying that this has to match. It's not that it's an anomaly matching, it's a new kind of matching.
Mm-hmm. Yeah, I agree with that. Thanks, Dominic.
But Dominic, sorry to derail the discussion. Does that mean that you think you could define this quantity in the microscopics using only the symmetry and not the Hamiltonian, and not any description of the degrees of freedom?
You need to specify the filling as well, right? The symmetries are totally boring. They're just translation and on-site charge conservation. Where is the filling fraction there?
Right. Whereas I feel to specify the filling is something that you need to do when you're dealing with this kind of particular system of hopping fermions. I'm not sure that that sounds like very focused on the particular degrees of freedom that you have.
I mean, the only ingredients you need a U1 symmetry and you need a translation symmetry. I mean, the details of the microscopic degree of freedom.
So how do you define nu given a U1 and a translation symmetry? What is nu for that?
That's the charge per unit cell. That's a fine definition.
Charge per unit cell. Maybe. I feel like that refers to the that refers to the fact that it's this particular these particular degrees of freedom interacting in this particular way. Anyway, we can talk later.
Okay, so let's see. I have a bit of time. What do you think, Luca? Should I spend 10 minutes to talk about a Fermi liquid?
Given how Clay has tried to derail your talk continuously, I think you should feel free to to take a bit of extra time.
Okay, thank you. So I'll try to be brief though. So we can skip 1D. Everyone knows about 1D Luttinger liquids and matching the filling fraction. But 2D is quite interesting. So let me just draw the picture again. So we have two momentum coordinates now. And if we're at some fractional filling, we're going to have some Fermi surface, which is now a continuous curve between the filled and the empty regions. And the system is very gapless in the sense that there's a continuum of low-lying excitations that you can make at every point of the Fermi surface. It's a bit like, so if I zoom in on the band structure here, it's a bit like at every point of the Fermi surface, I have a chiral fermion. So you can think about this as a chiral fermion with an extra index, a continuous index, theta. And in the theory of the Fermi surface, at least in the continuum theory of the Fermi surface, the particle number of each of these chiral fermions is conserved. So, and theta is conserved for every theta. So this is a very large symmetry. It's been called U1 to the infinity by Haldane, but it's not exactly like U1 to the infinity because you should think about n theta not as a function of theta, but more like an operator value distribution of theta. So group elements, if we actually want an operator, then what we need to do is we need to integrate n theta against some smooth function, alpha of theta, around this circle, around the Fermi surface. So alpha is a smooth map from S1 to U1. And so you can think of it as a loop in U1. And so the group of such maps is called the loop group, denoted LU1. And there's an anomaly associated with the symmetry, just like the chiral anomaly in one dimension. Now I'll remind you that in the chiral anomaly, a very simple way to see the anomaly is that if we apply an electric field, which is associated with the diagonal U1 symmetry, U1 left plus U1 right. I'm on the Zoom, please. That we will be moving electrons along this band and effectively creating axial charge by turning left movers into right movers. And a similar thing happens here, where if we apply an electric field, say we apply electric field in this direction, we're going to be depleting charges over here, and we're going to be filling states over here. So this anomaly can be made more precise in terms of threading a magnetic flux and seeing how the ends develop an interesting commutation relation. You can look in the paper. They give rise to this Cass-Moody algebra. But for now, let me just write down the solution to the anomaly polynomial. So I want to write some expression of a gauge field for LU1. And now one way to do it is, first I have to tell you what a gauge field for the loop group is, and you can think of it as a loop of U1 gauge fields, or equivalently, LU1 gauge field on X defines a U1 gauge field on X times S1, where the coordinate around the S1 is not really important for us. You can just set it to 0. And in order to express a 4 form, we need to express a topological term for 3 plus 1 dimensional SPT associated to this anomaly. What we do is basically take the 5D Chern-Simons term and do partial integration over the circle. Okay, so there's not really well-defined rules of locality for these objects. So we're just going to postulate that this is a well-defined topological term, and it does reproduce the anomaly that I mentioned. It reproduces this Cas-Moody algebra and various qualitative aspects of the behavior.
Ryan, what is the theta component of this gauge field? What does it mean?
Right, so theta, so if I want to think about a loop of U1 gauge fields, then I can define that. That defines for me a gauge field on X times S1, except that it only defines the components along X. So strictly speaking, a gauge field on X times S1 also has a component in the S1 direction. Now, in some applications of this anomaly, it makes sense to think about that as like the Berry phase around the Fermi surface. Because you can think of S1 as parameterizing the Fermi surface here. But it won't be important for the filling, for matching the filling fraction. So we can set it to 0.
Can you have large gauge transformations on that circle? So I mean, basically Wilson lines wrapping that S1.
Yeah, it's a good question. I think so. Certainly this anomaly polynomial is invariant under such transformations, but I don't know what the complete set of rules
You can
is.
have that, but it's not really a gauge transformation. It's actually just an element of a loop group. So it's actually a global symmetry transformation. But such things of non-trivial winding number are in LU1.
Mm-hmm. I see.
Thanks.
Okay. So let's talk about how we can, how the anomaly matching works for this for the loop group symmetry. So we want to compute the integral of our anomaly polynomial along this background, T2 times S2. But now we have this extra S1 that's part of the integral just because of the definition of omega involving this integral over S1. Now we need to define the background appropriately. So along the S2, we want to have a 2 pi flux. And along the T2, recall we want one of the loops to have one translation generator and the other loop to have the other translation generator. So what are these translation generators? Well, in terms of the loop group symmetry, it's quite simple to write down. The way that translation acts on every point in the Fermi surface, that point has the momentum just associated to where it is on the Fermi surface. So translation around X acts by e to the I integral kx of theta d theta. Whoops, forgot the operator here. And theta d theta, where kx is the, this parameterizes the Fermi surface, and similarly y underline picks up the y component of the momentum. Okay, so in order to
Can you explain one more time the manifold you're integrating over? It's supposed to be like this loop group direction times a 4D space-time.
Exactly, yeah. So this is describing an anomaly of a 2 plus 1D system. So it's a 4D integral but of a quantity that is itself defined as a, it's a 4D integral over this, right? So that's where the extra integration comes from. And around S1, the gauge field will be trivial, although the other components will depend on theta. And around T2, we want to have holonomies according to the translation generator. So we want to have one integral to be x lower, and we want the other integral to be y lower.
So T,
and then, yes.
Two-dimensional space that you originally had?
So the two-dimensional space that we originally had is doesn't appear here because this is a bulk partition function of the anomaly. So we've reduced the study of the filling just to a computation of the bulk partition function. So the original 2D space is not in this picture.
Okay, or could you just explain where this T2 and this S2 come from?
Yeah, so the T2, it's not very important, but T2 is the simplest manifold. I mean, it's not important that it's T2, but it's the simplest manifold where you have a single crossing here. Because remember that crossing came about from this commutation relation that picked up the filling fraction. So this manifold is devised so that you get exactly this commutation relation. Now there's some general relationship between manifolds you write down and then these commutation relations. And it turns out that this manifold is what you get in that case.
Okay, thanks.
Okay, thanks for the question. Okay, so we want to write down what this gauge field is. So basically, we can just write down something that has these properties. So it's going to have dx theta. We want to have kx theta holonomy around the x coordinate. So let me name. Let's take the coordinates to be x and y, and we want ky theta around dy, and then we want the 2 pi flux on S2. So that's what we get from the recipe. And we just compute a dA dA. So dA becomes dkx d theta theta dx plus dky d theta dy plus the 2 pi flux. And when we compute ADA dA, this 2 pi flux is going to split off. So we can do the integral like this. Right, so we just get a 2 pi out in front. And now we plug this in. And basically we're going to get 2 terms. We're going to get a term that combines this term and this term, and we're going to get a term that combines this term and this term. And when you put it together, d theta dx dy, I'm not going to be careful about the signs here, but we have dk x d theta ky minus ky d theta kx. And now these k's only depend on theta. They don't depend on x and y. So we do the integral over the torus. Torus just has volume 1 by how I've normalized it. So we're left with this 1D integral. And what you might recognize is that this is Green's theorem in the plane. And this is equal to the area enclosed by this curve, which is the Fermi surface. So indeed, the anomaly matching works given Luttinger's theorem, or from another point of view, if you take the anomaly matching as sacrosanct, then we've derived Luttinger's theorem by evaluating it for the Fermi liquid. So yeah, let me end there and thank you. Just to give you my summary. This is the equation we talked about or derived. And in the case of a Fermi liquid, this encodes Luttinger's theorem. So I do want to say that this is the interacting version of Luttinger's theorem. So thank you very much.
Awesome. Thank you, Ryan. Let's thank Ryan for the nice talk. And maybe let's take just one question now, if anyone has one.
Yeah, I have a question.
Mm-hmm.
So is this the statement about that relies on the Fermi liquid nature per se, or it's just tell you that the degrees of freedom, if they are on a line, then that line has to enclose a volume equal to nu. Does it apply to non-Fermi liquid if that state has a Fermi surface?
So we explore this this question in the paper about what we call ersatz Fermi liquids, where we consider. So I told you about the Fermi liquid, how it has this loop group symmetry. In general, you could define an ersatz Fermi liquid as just any system that has a loop group symmetry, or in higher dimensions, you'd want a more general kind of loop group symmetry that satisfies this anomaly matching equation, and then try to derive physical quantities from it, like quantum oscillations or what happens when you have boundary and so on. And these questions are very interesting. So the anomaly actually does give quite a few constraints just on all systems that have loop group symmetry and match the filling fraction like so. But more generally, systems that exist at some filling, even if they're not Fermi liquids, even if they don't have a Fermi surface, they don't have something like loop group symmetry, still, I expect that this anomaly matching equation is satisfied. So for instance, like at rational filling, where you might have a topologically ordered state, this equation is also satisfied, but it's only satisfied for irrational values of nu, because the translation symmetry can only be realized in such a way.
Thanks.
Does that answer your question?
Yeah, thanks.
Mm-hmm. Thanks.
All right, thanks again, Ryan. So let me